This is a continuation of factoring methods. We're going to talk about how to factor over not just integers, but real numbers and complex numbers, and tackle some more complicated questions. So in this example, we first of all look at common factoring, and there's nothing in common. It is a binomial, and we notice that x squared is a perfect square. The 3 is not a perfect square. So we would say that this cannot be factored over integers, and usually you would stop here. Let's continue on just to dig it a little bit deeper what can happen. I'm going to say that you can factor this using irrational numbers, because root 3 times root 3 will be the 3, and so we could say that it is a difference of squares. As long as we have the variable with a square and a negative, we could still follow this pattern. So we'll have one factor with a plus, one factor with a minus. We would have x times x would be x squared. We would have outside and inside multiplying and canceling. So we'll have negative root 3 with an x and positive root 3 with an x. So they disappear when you distribute this. And then positive root 3 times negative root 3 is negative root 9. And root 9 just becomes a 3. So this does actually end up working. So let's review the types of numbers that are out there. So at the beginning of your mathematical endeavors, you probably were counting using natural numbers. So naturally, you would start counting 1, 2, 3, not with a 0. So natural numbers are from 1, 2, 3, and so on. Then if you add a 0, which this is missing, so I've added it in here. So natural numbers union with or added with the 0 number, those are called whole numbers. Then if you expand 0, 1, 2, 3 with all the negatives as well, these are called integers. Integers, we use letter Z, not I, because I is reserved for imaginary numbers. Next, we have a set that's even bigger. We have Q for rational numbers. Why Q? Because they're considered quotients. So all of these integers, if you were to start to divide them, you would get rational numbers. And these rational numbers they could be decimals, but those decimals stop, or they have a repeating pattern. So these are called rational. Irrational numbers are the decimals that do not stop or terminate, and they also don't have any repetitive pattern. So you've seen root 2, for example, on the calculator, there is no pattern. You saw pi, and there's other numbers there. So this set right here is called irrational numbers, and we use Q with a bar to represent them. Why Q with a bar? So the bar represents that it's every other number that we know of that are not rational Q. So it's like they complement each other. So this set that has both rational and irrational numbers, that set is called real numbers. And it's misleading to think that there's other numbers outside of this. So real numbers are only either irrational or rational. Okay. Next set is just an enrichment. You in high school usually do not study imaginary numbers, but imaginary numbers come from when you have to do square roots of negatives. And so if you were to combine imaginary numbers with real numbers together like this, then that is called complex numbers, and we use letter C for that. So usually in grade 10, you will stop at factoring over integers. You do not have to go into irrational or imaginary numbers, but just keep in mind that you can factor over real numbers or complex numbers. So meaning you could use roots or even negatives under the root. So let me demonstrate with this example. We have no common factoring. It is a trinomial. The variable pattern works. So the first term is even exponent. Last term is no variable at all, so no exponent. And the middle term has half of this exponent 4. So half of 4 is 2, so that works. So that's a yes. And it is a complex trinomial because the first coefficient is not just 1. We have a 10 here. And we cannot pull out the 10 because then we get fractions. So what we're going to do next is we're going to do the crisscross factoring. So factoring 10, we can have 1 and 10 or 2 and 5. Factoring 18 could be 1 and 18, 2 and 9, or 3 with 6. This last number is negative 18, so we need to have one negative somewhere along each one of these combinations. I'm not going to place them until I know where it should go. So proceeding with crisscross, we're going to have 2 times 18, and then we're going to multiply that and then add with 5 times 1. Actually, I'd rather not multiply big numbers. Remember how I said in a previous video, you want to try numbers that are closer together first, and if that doesn't work, then you can try another combination. So let's try 2 with 6 multiplication. So 2 times 6 is 12. Remember that number in your head. 5 times 3 is 15. So if we have 12 and 15, and remember that one of these has to be negative, we need to get a negative 3. So 12 and negative 15 would probably give us this negative 3 as long as we put the negative on this top one. So let's try again. Positive 12, 2 and 6, positive 12. 5 with negative 3, that's negative 15. And negative 15 with positive 12 do give us this middle term. Then don't forget your variables. So this was just rough work, but technically this term, 2 and 5, they both have x squared. The reason why it has to be both x squared, not x with x3, is because if you were to do the crisscross, this would be, let's say if this was just x and this was x3, then it would be 2x multiplied with 6, so that would be 12 with an x, and this would be x to the 3, so 5x to the 3 with negative 3 multiplication, that would be negative 15x3, and those would not be like terms. This will have just x, this will have x cubed, and that would not give us this middle term. So that's why it's important to check your variable pattern, that is always going to be half for this particular reason. And a quick reminder, when you're doing trial and error, it's crisscross. When you record, it's top with top, bottom with bottom. Another reminder is that if we didn't find this combination right away, before going into bigger numbers, after you've tried 3 and 6, I would reverse the order on the shorter list. So this 2 and 5, put 5 on top, 2 on the bottom, and then try 5 with 2 with 3 and 6 one more time to see if you can get that to work before you go into like bigger numbers to try. And so when you record top with top, we have 2x squared with minus 3 as one factor, and 5x squared plus 6 as the second factor. Let's take this and put it back into our flowchart here. So this is the result. And let's see if we can factor any of these factors more. So each of these is a binomial. So we're going to say because the 2, the 3, the 5, and the 6, they're not perfect squares. So I can't say they're perfect squares. You would say you cannot factor more over integers. However, we've talked about the fact that you could consider them as perfect squares as long as the variable has even power here. We can actually continue to factor this more using irrational numbers, meaning square roots. So let's demonstrate that. We're going to use difference of squares setup. So this is what we had before. We're going to say usually you would stop here, but this is just an enrichment right now to see what happens if we use other types of numbers. So this is factored over integers. And this particular one is a difference of squares, so we can break it down, one factor with plus, one with minus. This is a sum of squares, and we'll leave it alone for now. So then we can say what multiplies to 2x squared? Well, x and x root 2 and x root 2 will give us 2x squared. Why? X times x is x squared. Root 2 times root 2 is root 4. Root 4 is just a 2. Now, why I place the x in front? Because if I placed it after, then it's going to look like potentially that the root is also on the x. So try to put the root part as the last in the term. Okay, so that would be factoring over reals, or these are irrational numbers, but they're part of real numbers. We could also do a little bit more. There's such a thing as an imaginary number. Imaginary number I is defined to be a square root of a -1. Now, if we square both sides, it's the same thing as -1 is equal to I squared. We're going to use this. How are we going to use this? We're going to take this 6 here. And because we can't use difference of squares on something that's not a difference, we're going to manipulate this a little bit. So this +6, you should all agree that negative times negative is a positive. So why is this useful? We're going to use this -1 as I squared. So this in front, this -1 right here would be I squared. -6 will stay there. So just change how it looks, -6I squared. So this is equivalent to this +6. So this bracket technically could be written like this using imaginary numbers. And now this is a difference of squares. So we can set up one bracket with plus, one with minus. We can have x root 5 on the first term of each of those factors, and I root 6 in the second one. So this is now factored over complex numbers. And just to tie it to something that you will be learning eventually, there's a fundamental theorem of algebra that states the following. Any polynomial of degree n, so here we have a polynomial of degree 4, will have exactly n roots. So we will have exactly 4 roots or solutions. These roots can be rational, irrational, or complex. And so you could definitely tell we're going to have some irrational and imaginary numbers or complex numbers as the solutions in this. Just to keep in mind though, usually when you're asked to factor, you just stop at this line right here.